Let's directly start our first lecture on linear differential equations and the matrix exponential. Okay, let all my lecture note will be like this. By the way, I'm going to write on the lecture note and derive everything for you. And it's occasionally I will do some coding in class. That's the way I'm going to teach you. Okay, the first lecture is about linear system and the matrix exponential. Why we care about this, motivations, right? So most engineering student systems involve, including most robotic systems, are modeled by differential equations. Okay, differential equation, if you in discrete time become difference equation, even what's happening function. All right, I gave an example here, the dynamics of 2R robots. That's from Modern Robotics book. So this is nothing but a differential equation. This is the differential equation. Differential equation in variable theta. Okay, I don't know why it's two. Okay, in differential in theta, and then involves second order, right? Involves second order derivatives of theta as a function, right? And it's a nonlinear differential equation that used to describe the dynamics of 2R robot that we're going to learn how to derive it later in this class. Okay, not only dynamics, it turns out through theory, exponential coordinates, or the things that I care the most, product of exponential, all of these things, actually, they are based on a differential equation view of robotic kinematics. I don't think, but just keep that in mind. I don't think you can understand it now, but I just want you to know that why we need to cover this is the kinematics, the DH, whatever they are trying to represent. Essentially, you can use a differential equation, differential way to approach them. That gives you a twist or other things, right? So that's why we need to understand differential equations, especially linear differential equations. 线性微分方程, right? I think that's very simple. Most of you have learned that from your undergraduate class. All right, let me find my notes. Okay, so these are a set of differential equations. The two examples. This is example 1, and this is 2. Okay, let's look at these equations. The first one is what? This is a coupled. It is a coupled, two coupled. Let's say two coupled first order different ODE. Okay, they're coupled ODEs, right? And for those kind of differential equation, this one involve two differential variables, x1 of t and x2 of t, right? What do I mean by solve the differential equation? You need to solve these two functions of time that satisfies at any given time this differential equation. That means you solve it, all right? So for advanced study, for modeling and control, even for robotics, oftentimes we want to put this into a more standard form in vector form, okay? So let's define it. To put two variables, these are scalar variables. I can put them as a two-dimensional vector, right? That's fine, right? And so this equation describes nothing but the differential evolution of this vector in R2. Okay, this is in R2. So if you take derivative of this so-called state vector, and that becomes x1 dot and x2 dot. Let's just warm up with more derivations, okay? Let me finish this before we take a break. This will give you what? If I write this x1, x2, t, this is what? x1 dot equal to negative x2t, right? So that's 0, negative 1, if you are familiar with matrix vector multiplication, right? And the second one is x2 dot is negative 1 x1 and negative 1 x2. Okay, so that's the standard, more compact form. So when I write this form, I essentially write away like x dot equal to a times x. Somehow I drop the dependence on t when it is clear from context. Okay, so where this one is my A matrix, okay, which is a constant, which doesn't depend on time. Now you have seen this, a standard differential equation you may have seen in undergraduate class, can be written this function, this kind of vector form, all right? And sometimes your equation may involve higher order derivatives. Okay, for example, these two coupled equations involve two variables, right? Two variables. You need to solve for y, you need to solve for z, two of them. But for y, you have second order derivative. Okay, for z, you involve first order derivative. So essentially, we don't like high order derivatives. Okay, we want to make sure everything is about first order derivative. So we can define that x1t equal to y of t, x2 of t equal to y derivative of t, and x3 of t equal to z of t. Okay, we can introduce a vector which is three-dimensional. I can say x dot t equal to x1 dot t, x2 dot t, and x3 dot t. All right, x1 dot t is yt. Yt is, it's y dot, right? Y dot is x2. So if I put them in the matrix vector form, for linear system, I can always do this. For nonlinear, I can't. X1 dot equal to x2. So if you do the multiplication, this row will be 0, 1, 0. X2 dot is 2. X2 dot is y double dot. Y double dot is negative z, which is negative 1 here, right? For the other one is x3t is z dot. Z dot is negative 1, which is this one, so negative 1, 0, 0. All right, so in this way, I also have x dot equal to, this is my A times x. Right, for all the system differential equations, I can make it a state space form. I think most of you have learned about this for undergraduate class, so why I'm so quick about it. If you haven't seen this, you have to believe me, all the linear differential equations, all the ordinary differential equations, you can put it in a state space form, which is a first order ODE with vector variables. Okay, it's of the form x dot equal to ax, that's for linear case, okay? All right, so why we care about first order that much? It's very easy to solve a first order differential equation in scalar case, okay? You can generalize that intuition to, you just make sure a point now, not on the line now, it's in the Rn, okay? N-dimensional space. If you want to describe a point motion, what you need is only the location of that point and also its velocity, how fast and which direction it's moving, then you know infinitesimally where it will be at next time, right? And then next time you specify the velocity, you know other place, how its motion is. So reduce high order derivatives to first order, and by sacrificing the sacrifice you make was what? Is try to increase dimension of your system. Okay, so we can always write like this. And this part, the static form, this part is called a vector field. For you to know, it's just velocity. the vector velocity of your state vector at this point, at this place. Okay, so this is a very special case for general dynamical system. A general dynamical system will be derived or described by this x dot equal to a nonlinear, potentially nonlinear function of xt. And I want to make sure that if fx equal to ax, if this nonlinear vector field is a linear function of x, then this becomes what? Linear system, which is x dot equal to ax. The two examples we gave you before is all about linear system. And that's a special case of this general dynamical system. And this vector field, if I just try to introduce my notation gradually, all right? I will write this like this. What does this mean? It's a function that maps from Rn to Rn. Do you know what it means? If you give me n-dimensional vector, the f will return an n-dimensional vector to you, right? That's a mapping from Rn to Rn. Later, I will have mapping from Rn to Rm to Rp, whatever, okay? So it's nothing but map an n-dimensional vector to an m or p-dimensional vector, okay? A special term I want to give you a remark, maybe not that important, but for just to clarify my notation. So this system is called autonomous. Okay, let me explain that a little bit. I don't think this term can be defined that precisely. This autonomous differential equation means f, the function, the vector field, does not depend on, let's say, does not depend on, I would say, non-x variables. In other words, the function is fully specified if you tell me your state vector. Okay. Let me ask you this question. Let's say x dot equal to ax, that's my linear system. This is an autonomous system in the sense that my vector field depends only on x. Okay. What about ax plus b? Do you think that's autonomous or not? Well, some people may think not, but well, it is autonomous system as well, right? So this is the function of x. If you tell me x, the function value is completely determined. You see what I mean? It does not depend on any other things. For example, t, time. It does not depend on time. All right. So how to check it's autonomous or not? So this function, the vector field, the velocity only depends on the state vector. So if you tell me state vector, the velocity is completely determined. Okay, that's autonomous. Means a non-autonomous system in general can be written like this. Okay, it not only depends on x, but also depends on other things. And why I write a t here, that's become time varying. So this one is captures all, I would say, non-x dependence. Okay. For example, I would say x dot equal to ax plus 2 of t, time. So if you tell me x, for example, if I draw let me see. If I draw, I don't know where I can draw it. So suppose my state space like this, okay? If you tell me that's my location, can you completely tell what's the velocity? No, it depends on time, right? The next time we visit here, you have different velocity if your vector field is like this. So it becomes non-autonomous, okay? It's also, well, depending on how do you categorize the vector field, this is also time varying, okay? Another example is ax plus d of t. Is this autonomous? What depends on d of t, whether d of t is constant or not. Okay, if d depends on t, then it's not. All right. Okay, so it's non-autonomous system. Just clarify the notation and also terminology a little bit. And what we're trying to learn is a control system. A control system is a special non-autonomous system, in the sense that the vector field does not only depend on my state, where I am. So how you evolve does not only depend on where you are, also depend on another thing which we call control, right? Depend on external variable control. Control purpose is what? Mathematically, you try to influence your velocity instantaneously. See what I mean? Okay, so for example, I can say x dot equal to ax plus sine u. Okay, that's a non-autonomous system, right? Is this autonomous or not? I drop all the dependence on t now. Okay, is this autonomous or not? Not really, because this is a function of x. If you tell me x, you cannot fully specify the function yet. You have to know what u is, right? These two jointly tells you the velocity or vector field. So that's a example. Okay, and for so far, later we'll talk about how to analyze general nonlinear control systems. But for now, and for this class, maybe first half of it, we will mainly focus on, we only need, I'll say, not focus on, only need the linear system result, okay? For general linear control system, this is general linear control system. And in this case, this is my, can you tell me what's the vector field function? The state is x, this is my state. The control is in Rm, y is system output, and this one is my vector field. So vector field function, if you write in terms of its immediate argument, is nothing but ax plus bu. Okay, that's my vector field. It's linear with respect to x, it's linear with respect to u, when the other argument is fixed. Right, so that's a linear system, the vector field, the control influence the vector field linearly, and also control, state depends on the, determine the vector field also linearly. Oh. Let's go back. And so the system here, if you look at this is the output equation. This one, I will want to point out, this one is a static relation. What do I mean by static? There's no differentiations, right? If there's no derivatives, this is a static relation. It's a static function. No dynamics, nothing changed, right? So if you know x, then you immediately know y. Or know x and you immediately know y. So the order of the derivative, the order of differential equation is determined by the dimension of state vector x. It doesn't matter how big y is. So how hard you can solve the system depends on the dimension of x, because that's the only thing involved derivatives. Okay. I think that this is my quickest path to this general linear control systems. Okay, it's essentially a non-autonomous dynamical system. All right, and my question, or today, maybe a little bit next time, we're trying to derive equations for this general linear control system. Okay, in other words, how to solve this ordinary differential equation if we put it into this standard state space form. Okay, that's our question to need to answer. It turns out the key, we can find, by the way, so this solution, the linear system, there is a analytical solution we can write down explicitly. Okay, and you are going to learn how to do it. It's very useful. It turns out robotic kinematic dynamics also can be written as a solution to linear system. That's why we cover that. Okay, to solve the equation, the key, I'm not going to tell you the answer and then stop, ask you to program or implement. I'm going to derive the solution for you. But we have to start from somewhere. That somewhere is we have to accept a very important theorem from real analysis, is the existence and the uniqueness of general ordinary differential equations. Okay, once we know this one, and we have our way to find the solution. Okay, I don't think we need the most general version, and this is the version we need. But before that, I need to just cover some very basic terms in case some of you are not familiar with it. Have you learned about continuity? 我们的本科一般学calculus 是怎么讲这个连续方程 function，continuous function. How do you define continuous function? 刘奔，忘记了。Okay, you didn't learn real analysis, then you learned calculus. Okay. Anyway, so then you haven't heard about Lipschitz continuous. Have you or not? Lipschitz? Okay, what we need to define this, okay? Let's say, I'm not going to define it in the most general math form. I don't think that's needed at this stage, but I require you to know that, by the way. I can draw figures for you, okay? Such a function of x, suppose this is, I would say, smooth, okay, roughly speaking, right? Roughly. It's not only continuous, you can take derivatives, okay? This is a smooth function. What about this function? Is this continuous? It is continuous, right? But not smooth. This part you cannot take derivative. So it's this one is continuous, still continuous, but not smooth. All right. I'll give you another function. I'm not sure whether you heard about this term. And you know what this circle means, right? This kind of function. It's this continuous? No, this part there's a jump, right? But only at this particular point there's jump. At any other location, if you look at this interval or that interval, they're continuous, right? So this kind of a function is called piecewise, 分段, piecewise continuous. You see the term? Okay. Now let's look at another definition, which is called Lipschitz continuous. What does this mean? You should be able to kind of see what it means from the math. Can you read this equation? Or does this equation make sense to you? A function g is called Lipschitz over domain D if there exists, this means exist. Okay, if there exists a finite, that means finite, right? I'm going to read that for you. There exists a finite L such that this inequality holds. Okay, I won't read this equation, but does this make sense to you? What does this mean? So if you x moves a little bit from, if you move away from x, you move to x primes. There's another point, okay, in D. Your function value will be changed, right? Your function value will be changed. It just say the function value changing, the change of the function value is bounded by a constant times that. If in one dimensional, it will be just a derivative, somehow it's bounded. upper bounded. In high dimension, it's slightly different. I'll give you an example about Lipschitz continuous is more, is required. If it is not continuous, definitely not Lipschitz continuous. Let me give you an example. Let's say gx equal to square root of x, absolute value of x. So if you draw this function, you can take derivative of it. Okay, but let's just draw it. Because it's the absolute value of x, so this function is well defined for the entire real line, on the entire real line. Okay, to look at this, it's almost like that. Okay, that's the function shape. It's not Lipschitz. This is not Lipschitz. Why? Because around here, as you get closer to the origin, the change or the slope of your function change is become infinite. There's no bound. There's no single bound you can. So if you zoom in here, I don't think I draw it correctly, but if you just move, let's say you're infinitesimally close to the origin, you move a little bit, let's say from 10 to the -6 to 10 to the -8, but your function value change is really, really huge. Okay, there's no bound on this ratio, so it's non-Lipschitz. Okay, non-Lipschitz is not good, right, for differential equation. Of course, most of the problem we have should satisfy this. Okay, so the uniqueness result that we're going to use, I think that's maybe the result, key message you need to know, even outside this class, that's a useful fact, is that suppose I have a nonlinear dynamical system. This is a differential equation. This is non-autonomous differential equation, and with initial state or initial value. This is called the initial condition, right? The initial condition. That's shorthand notation for initial condition. Has a unique solution whenever f is Lipschitz in x and piecewise continuous in t. Okay, that's the result you have to keep in mind. I don't want to prove it for you, but I think that we can accept as a fact. So what do I mean by this function is Lipschitz in x? So you view that as a function of x. That means for arbitrary t. So f is a function of x and t, right? And f(x) prime of t should be less than L times x minus x prime, and for all t. For all t in the range of our interest, maybe from some t0 to t final, okay? Anyway, so for arbitrary t, this function is Lipschitz with respect to x. And with respect to t, is piecewise continuous, like this particular figure that we saw before, okay? So if you hold x fixed, then it's a function of t. That function of t should be piecewise continuous with respect to t. And vice versa, if you fix t doesn't change. You fix the value t equal to 1, 2, 3, 4, 100, whatever, as long as within the range, then it's a function of x. And that function of x need to be Lipschitz. Why x is so important? Because x is a state vector. Okay, it's not arbitrary, another variable. Okay, so that's give you a unique and it always exists one solution and it's unique. All right. So what do I mean by exists a solution? Let's say solution to this equation. Let's call it 1. Solution to 1 really means you need to check two things, right? One is the initial condition has to be satisfied. When you solve a differential equation, the first thing to check that solution you gave or proposed need to satisfy initial condition. What do I mean by that? Is x at some initial point, t0, need to be equal to the given initial condition x0. That's exactly the initial condition. 2 is x dot of t. Of course, I'm just writing this. Satisfies this equation for all t. You start from time 0 at a particular point, and after that, you always follow the vector field velocity. But that means you satisfy, you solve the differential equation. That's our 5 minutes existence uniqueness from ODE. I like a lot of more stronger version, okay, locally Lipschitz, all the other things. But I don't think that's useful for you. All you need to know is this theorem, roughly it's fine, okay? And in fact, what we really care about is the following. Is this theorem tells us a corollary is a linear system of this form always has a unique solution, has one solution and also has a unique solution for any piecewise continuous input UT. Can you prove it? Zhang, can you prove it? How to prove this? When I say the corollary means it's a consequence of the theorem, right? So I know in general, if I have this nonlinear, whatever, linear, nonlinear ODE, I know that when it exists a solution or uniqueness property holds. Now I just need to check whether this is my vector field. What is my vector field here? Let's say if I write this vector field, I'm not sure whether you even can, oh, sorry. My vector field function is a function of x. Let's say if I want to make of this form, okay? It's a function of x. Another thing, I capture all the other things in terms of t. Okay, so this thing, it will be a times, to further confuse, not confuse you, let's just say x plus b times u of t. Is this vector field depends on t? Yes, of course. All the vector field depend on t, but that dependence sometimes is through x. That doesn't count, right? So whenever x is fixed, it's also depend on t. That we care about more, okay? So that's the part from ut, right? So this is my vector field, if I write in this notation. And if I check whether it's, let's use this one. So I can check condition, right? Suppose the first one is, if I say f x t minus f, let's call the head, okay? Defined like this. X prime t, what is it? Is a times x minus x prime. And that's it. U got canceled, right? So this one, if I take a norm, that's a vector norm, right? And this vector norm is to be less than a norm times this one. Okay, suppose let's use a Euclidean norm, right? This will be my L. Okay, it's, of course, it's a linear function. It's a Lipschitz continuous. You can think about that matrix norm is the maximum of the slope of your function of the mapping, right? And also, I want to say whether this guy is piecewise continuous in T. So it's a continuous, this one is what? Ax plus b of ut. If I fix x, this is a fixed. It's a function of t. That function of t through u. Okay, through this variable u, right? So overall function is smooth and continuous with respect to u, and the u is piecewise continuous. So this one is also I had a vaping argument, okay? This is also piecewise continuous in T because U is piecewise continuous, right? Or sometimes call this piecewise continuous in T. All right, so that's the somehow a proof, if you want to call, I don't call it proof, maybe an argument, reasoning, that why this general linear differential equation has a unique solution, okay, for piecewise continuous UT. Piecewise continuous, all right. And you start to have your first homework, as I mentioned, the key is homework. I want you to prove or derive conditions under which this time-varying system has a unique solution. The only difference here now is A is not a constant matrix, is time dependent. Okay, can you prove that? So I have my philosophy, as I told some student before. In class, I do the easy one, you do the hard one at home, all right? So that's the only way you learn. I gave you a simple example to illustrate how to use the concept or result, and you do some hard work at home, right? That's your first homework problem. We're gradually increase the level of difficulty throughout the semester. That's the first one, okay? Any questions so far? What do we get so far? Yes. In the core domain, there is no initial. Yes. Oh, yeah, of course. Yes, of course. That thing is not that crucial, so I didn't. Yeah, there's the initial condition x. For here is 9, x 0 equal to x 0 is fine. Time 0 is there's, of course, there should have an initial condition. All the differential equations should have a initial condition before you can even think about solving it. Okay, so far all we have learned is that what? This is so-called linear system, control system. We have learned this system has a unique solution, okay? And we didn't tell you what the solution is yet, right? Now our next job is to find the solution, derive the solution, okay? For which we need to define or introduce the so-called matrix exponential. How many of you have heard about matrix exponential? 叫什么？指数矩阵指数。Okay, matrix exponential is a fundamental for solving a linear system in state space form. Okay. So let's get started with the matrix exponential. Okay, let's recall a little bit. So for our goal, ultimate goal is to solve an arbitrary kind of general linear ordinary differential equation. For a control system, this dt is, for linear control system, it's b times ut. All right, in general, dt captures everything else. Okay, I'm going to solve this equation. It turns out the key is to derive solutions to this autonomous case or homogeneous case, so-called. Okay, so x dot equal to ax. If we can solve this one, everything else become a standard exercise, and you're going to do that later. Okay, for now, I will teach you how to derive solution for this x dot equal to ax when x is a vector, a is a matrix. Okay, a is a constant matrix. This means n by n matrix. Okay. Again, we will give a initial condition. And this condition, of course, is also in an initial point in Rn. how to solve this equation. And the key is that by existence and uniqueness theorem, we know this ODE always have a unique solution. That's very important. That means whenever you find a solution, that's it. There's no other choice. Now it's just how clever you are. Whether you can somehow magically find a solution and satisfies the differential equation. Okay, it turns out the solution can be found analytically with the so-called matrix exponential. That's why we need to introduce matrix exponential. Let's, before talking about even matrix exponential, let's recall a little bit about exponential Euler number, okay? The scalar case. I assume you know this solution. Do you or not? Ruben? If this is a scalar case, do you know the solution?
Solution is
This is the ODE or not?
yes,
It's the ODE.
Yeah.
Initial condition. These are scalar, okay? Everything is scalar. This ODE has a unique solution or not?
Unique solution.
Because we have a more general theorem already prove it, okay? Now I'm asking you, what is the solution? I don't know whether you can derive it, but at least you memorize, I think, the solution, right? Say that again. E to the A times T. That's it?
Yeah. 来加上出手式。
How to add the initial condition?
E 的 AT 乘以 Z
Times J0. Okay? Is this the solution? Of course you should. Have you learned this, by the way? You should, right? Let's prove it. I like prove. Of course, it's too simple because I only prove the simple ones in class and you prove the hard one at home, right? That's very simple, right? What do I mean by a solution? It has to satisfy two things, initial condition and the vector field. Okay, so in this case, let's first check. First one, check IC, initial condition. So that means Z at time 0 is E to the 0, which is 1, right? Times 0, Z0, which is 0. Excellent. We checked the first one, you got half of the grade. The second one is check the vector field. This is 0, by the way. Vector field is Z of dot. Okay, Z of dot. If you plug in this expression, Z dot equal to what? E to the AT. So you need to, this one is a constant, right? So it's thus A times E to the AT times Z0. Is that true? Okay, if you look at, sorry, this is, let's do this. Let's say I plug in this equation, right? So E to the AT times Z0 prime, okay, equal to A times this. So this one is our proposal of ZT, right? So that means Z dot equal to A times this one's also our Z. So it satisfies the differential equation. And you propose something and you prove it satisfies the equation, both initial condition and also differentiation rule. Then you prove it. You find the solution, and it's unique. You don't need to look for others. Okay. Does this really make sense to you? Why this happens? Because there's a magic number here, E, right? You remember this is what this means? E is the so-called Euler's number. Okay, how is defined? To remember, there's various ways to define E, okay? But one of the most fundamental ways defined as D number, okay? D number that is such that E to the X prime equal to E to the X. Okay, you can check, right? 2 to the X prime. You can take the derivative if you find out it doesn't equal to 2 to the X. Right? This is 2, this is 2. You can try 3. It doesn't work. You find out, oh, E is the magic number such these two things are equal. E is just defined in terms of as solving the differential equation we care about, right? How do we define this one is this? If you look at this, that means if you take the limit, let's say, you all know how the differentiation is defined, right? So E to the X derivative, how to compute this? So EX plus H minus E to the HX divided by H go to 0. So that's the E to the X derivative with respect to X. If you perturb X a little bit, okay, that's the derivative with respect to X. And we should satisfy this. Is that true? This one directly implies E to the H minus 1 divided by H if you divide by E to the X, because the limit is with respect to H, not with respect to X. So X is almost like constant, right? So you divide by everything by E to the X is like that, has to convert to 1 as H go to 0. So that means E to the H has to convert to plus 1. That means E to the H has to equal to limit H go to 0, H plus 1 over H. That's one version of it. Of course, you can make N to the infinity and things like that. All right. So this all gives you some kind of number, and make sure that number is 2.7. I forgot, but something about 2 and below 3, right? That's how E was defined. E is the magic number solve some kind of differential equation. Okay, all right. E can be defined in many other things, and one thing that we engineering people like the most is Taylor theories, right? Taylor expansion. E can be defined as this Taylor expansion. Do you remember the Taylor series expansion of E to the X? That's very important. By the way it's constructed, it automatically can prove it, by the way. If I construct or define this way, E to the X prime, you just look at the right-hand side. This one is 0, this one is 1. This guy takes 1, divided by 2 factorial, it becomes X. And it's perfectly aligned. Okay, if you look at those numbers, it's almost like you want to take derivative. I'm not sure. If I see this equation, I want to take derivative automatically because it's cancel and this one take derivative become the previous term. So it's E to the X as well. So this is the Taylor expansion. And Taylor expansion of E to the X, this equation can be used to generalize the exponential to many, many things. For example, I'm not sure whether you remember, okay, you can define complex exponential, E to the Z. Can we? Of course. We can define. Define means there's no why, I just want to define it, right? It will be useful, but I just want to define this. I replace this X with a complex number, then I have the exact same formula. Okay, this power series is also well defined for all Z on the complex plane. So this is nothing but a function of what? Of z. Okay, this is the exponential function of z I define in terms of power series, and this power series always converges no matter what z I plug in. Okay, that's this case. And in particular, if I plug in, let's say, let z equal to the imaginary axis, j times theta, this is the imaginary unit. What I have is you plug in this, you have this expansion, right? If you remember sine theta expansion, Taylor theory expansion is what? It's x minus q plus x5 factorial plus x7 factorial. Cosine theta is 1. You should remember this, I think, okay? Is that true? Yes, plus goes on, right? If you compare terms, it's just this one is nothing. Sorry, this is not x. I mix my notations. This is the theta. The theta, and theta. And this is nothing but the imaginary terms of this term. So that's why you have e to the j theta equal to cosine theta plus j times sine theta. And this is called what? Euler's formula. Right? Euler 公式 yes.
x 为10的时候，在 x 里不停的看着那之后这个 z 为负数的时候，它没有限定条件的时候，哪一个？
不，这个 Taylor series 是不管在哪儿都可以。这个 x 可以是 for any x belong to R、C， 都是等的。
那它后面写 around x。
写错了。你这就无所谓了，不要这句话不要，好吧 ？OK。你可以你不用进，不用 close and 你可以要这句话。这个 x can be arbitrary x，right？ 你可以说，当它进的时候，你可以 approximate ignore higher terms，but if I keep all the terms, that's true, absolutely true for all x and for all z. Okay, why I talk to you all of this is a little bit about history, a little bit about basic calculus, because that will make sure you have gradually accept how to define matrix exponential. Okay, so I can define this way, and that's how this connect to other knowledge you may have heard about. And for matrix, I can also define the so-called matrix exponential. I'm using the same formula. Okay, similar to the complex case. In order for this definition, this is to make sense. All you need is to plug in some kind of number or variable that you can do multiplications or raise to the power, right? As long as z squared, z cubed, z raised to the power n is well defined, I can define this function, right? This is a function of z, then I can define a function of matrix, which is called matrix exponential. That's exactly a matrix exponential. And for this case, this is n by n matrix. This is also n by n matrix. Okay, that's it. Let me take 2 minutes to give you one example so that we can continue next time. So, okay, suppose my A is like this. Okay, a very simple two-dimensional matrix. So A squared, it turns out A squared becomes all 0. This matrix is called nilpotent. Okay, this somehow you take square, become 0. And then a cubed is also 0, right? So by this definition, I can directly compute e to the a is I plus 0, 1, 0, 0, which is 1, 1, 0, 1. That's a matrix exponential for this matrix by this definition. Okay, it turns out the definition of this allows us to define the solution to x equal to ax, similar to the case scalar case that we're going to continue next time. Okay,